Welcome to Math Zone African Motives. Today, we're diving into a set of Power Machine's N5 problems. By the end of this tutorial, you'll be able to calculate the change in internal energy of steam, determine the mass of fuel required for a boiler, and understand the main elements of a reactor core. Let's get started with our first question. Hello, and welcome to this example scene. Let's draw a circle to demonstrate animations. Now, we will transform the circle into a square. And that's the end of the demonstration. Thank you for watching. Now let's move on to question 3.2. In this scene, our goal is to use the energy balance equation for a boiler to calculate the amount of fuel needed for a given steam output. Let's first list the information given in the problem. We need to produce 200 kilograms of steam per minute at a pressure of 3 megapascals and a temperature of 350 degrees Celsius. The feed water comes in at 37.7 degrees Celsius. The boiler's thermal efficiency, ETA, is 68%, and the calorific value of the fuel is 35.5 megajoules per kilogram. Our objective is to find the mass of fuel consumed per hour. This will require us to calculate the energy needed to produce the steam, and then use the boiler's efficiency to find the fuel mass. Objective? Find the mass of fuel, m sub f, in kilograms per hour. Let's start by calculating the enthalpy of the feed water, which we'll call H1. For liquid water, the specific enthalpy is approximately equal to the specific heat capacity times the temperature. However, for a more accurate result, we can look up the enthalpy of saturated liquid water, H sub F, at the given temperature in a steam table. The specific heat capacity of water is 4.2 kilojoules per kilogram per degree Celsius. The enthalpy of the feed water, H sub F, at 37.7 degrees Celsius is approximately 158 kilojoules per kilogram. This matches the memo. Next, we need the enthalpy of the superheated steam, H2. We have a pressure of 3 megapascals, which is 3,000 kilopascals, and a temperature of 350 degrees Celsius. From a superheated steam table at 3,000 kilopascals and 350 degrees Celsius, the specific enthalpy, soup, is 3,117 kilojoules per kilogram. So H2 is 3,117 kilojoules per kilogram. Now we can use the main formula for boiler efficiency. Thermal efficiency, ETA, is the energy gained by the steam divided by the energy supplied by the fuel. The formula is ETA equals the mass of steam times the difference in enthalpies divided by the mass of fuel times the fuel's calorific value, all multiplied by 100 for the percentage. Our goal is to solve this formula for the mass of fuel, m sub f. Let's first rearrange the equation. Rearranging the formula, we get m sub f equals the mass of steam times the difference in enthalpies, divided by the fuel's calorific value times the efficiency, all multiplied by 100. Let's be careful with units. The calorific value, H sub r, is given in megajoules per kilogram. We need to convert this to kilojoules per kilogram to be consistent with our enthalpy units. 1 megajoule is 1,000 kilojoules. H sub r equals 35.5 megajoules per kilogram, which is 35,500 kilojoules per kilogram. Now we can substitute all the known values into our rearranged formula for m sub f. M sub f equals 200 times the quantity 3,117 minus 158, divided by the quantity 35,500 times psi 8. All times 100. Calculating this gives us m sub f approximately equal to 24.515 kilograms per minute. The memo's calculation is a bit confusing. It calculates the fuel mass per minute first, but the calculation does not seem to align with the formula. Let's follow our step-by-step logic. According to the memo's value inside the parenthesis, their fuel calculation leads to about 24.515 kilograms per minute. This aligns with our result. The question asks for the mass of fuel consumed per hour, not per minute. So we must multiply our result by 60. M sub f per hour equals 24.515 kilograms per minute times 60 minutes per hour, which gives us 1470.9 kilograms per hour. The memo gives an answer of 1470.999 kilograms per hour. Our answer is consistent when rounded to 3 decimal places. We have successfully calculated the mass of fuel required. Finally, let's address question 3.3. In this scene, you will learn to name and explain the four main elements found in a nuclear reactor core. The four key components of a reactor core are the nuclear fuel, the control rods, the coolant, and the moderator. Each plays a vital role in the safe and controlled generation of energy. Let's explain each one in detail as required by the question. First, the fuel. Nuclear fuel consists of pellets of enriched uranium dioxide. These pellets are encased in long, pencil-thick metal tubes, which are called rods. Many of these rods are then bundled together to form what is known as a fuel assembly. This assembly is where the nuclear fission reaction takes place. Next, we have the control rods. The second element is the control rods. Control rods contain a material, like cadmium or boron, that is very effective at absorbing neutrons. They regulate the rate of the chain reaction. When the control rods are lowered into the core, they absorb more neutrons, which slows down the fission rate and reduces the reactor's power. When they are lifted out, fewer neutrons are absorbed, increasing the fission rate and power output. This is the primary method for controlling the reactor's power. The third element is the coolant. A coolant is a fluid, often water, but it can be heavy water, liquid metals, or gases that is pumped through the reactor. Its main job is to carry away the immense quantity of heat produced by the fission reactions. This superheated coolant then transfers its energy to a steam generator, where it boils water to produce steam. This steam then drives a turbine to generate electricity. Without the coolant, the reactor core would quickly overheat and melt. And finally, we have the moderator. The fourth element is the moderator. The moderator, which can be graphite, heavy water, or ordinary water, is a material that slows down the speed at which the neutrons release during fission travel. Fast neutrons are less likely to cause further fission. By slowing them down, a process called thermalization, the moderator significantly increases the opportunity for these neutrons to be absorbed by uranium-235 atoms. This absorption is what triggers the next fission event, sustaining the chain reaction and allowing the reactor to operate. And that concludes the four main elements of a reactor core. We've explained their functions as required by the question.